solubility product constant, or KSP. When we talk about our solubility product constant, we're looking at another type of equilibrium constant. And in this case, we're looking at the equilibrium constant for the dissolving of a slightly soluble salt in water. So we'll use silver bromide as our first example. And if we take silver bromide and dissolve it in water, it's going to just a very small degree, break up into its ions. And we're going to establish an equilibrium between the rate of the dissolving of the silver bromide, going towards the right in the equation, and the rate of the precipitating of the silver ions and the bromide ions going to the left. And once we establish that equilibrium, we're going to be able to write a K expression. And remember that K expressions are written with the concentration of the products raised to the power of the coefficient in the balanced equation over the concentration of reactants raised to the power of the coefficient in the balanced equation. And we don't include solids and liquids in our K expressions. So our equilibrium expression for the dissolving of silver bromide would be KEQ equals the concentration of silver ions to the first times the concentration of bromide ions to the first. And we're going to give this KEQ a special name, and we're going to call it KSP, or the solubility product constant for silver bromide would be equal to the concentration of silver ions times the concentration of bromide ions in that saturated solution. So I'm going to give you a chance to practice writing your balanced equations for dissolving salts in water and then writing the KSPs. So I want you to pause the video for just a second, write out your balanced equations for the dissolving process, and then write your KSP expression. So let's see how you did. If we look at our lead chloride, it's going to break up into 1 mole of lead ions for every 2 moles of chloride ions. So our KSP would equal the concentration of lead ions times the concentration of chloride ions squared. If we were to take silver chromate and dissolve it in water, we're going to have 2 moles of silver ions for every 1 mole of chromate ions. So our KSP would equal the concentration of silver ions squared times the concentration of chromate ions. And if finally we were to take bismuth sulfide and dissolve it in water, we would get 2 moles of bismuth ions for every 3 moles of sulfide ion. So our KSP expression would be the concentration of bismuth ions squared times the concentration of sulfide ions to the third. So now let's look at a problem. We want to calculate the solubility of sulfide ions in a saturated solution of bismuth sulfide. When it says solubility, it's looking for molarities. And when we look at problems like this, the first thing we want to do is we want to write the balanced equation for the dissolving of the salt in water. We want to write our KSP expression. And then, if we're trying to find the concentration, we look up the KSP on a table, and we can calculate the concentrations. So let's look at what we do. First, we take that bismuth sulfide and we break it up into its ions. We balance the equations, so we've got 2 moles of bismuth ions for every 3 moles of sulfide ions. We write our KSP expression, so the concentration of bismuth ions squared times the concentration of sulfide ions to the third. And then we can look up on a table what the KSP for bismuth sulfide is. And when we look at that number, it's 1.8 times 10 to the minus 20. That's telling us that bismuth sulfide is not very soluble in water at all. Now we're going to plug in our values for our bismuth ion and our sulfide ion. But since we don't know them, we're going to have to plug in X values. For every 1 mole of bismuth sulfide that dissolves, we're going to get 2 moles of bismuth ions. So we'll plug in 2X for our bismuth ion concentration. And for every 1 mole of bismuth sulfide that dissolves, we get 3 moles of sulfide ion. So we're going to plug in 3X for our sulfide ion concentration. Now we have to do a little bit of math. We've got 2x squared times 3x to the third. So 2x squared is going to give us 4x squared. And 3x to the third is going to give us 27x to the third. So we'll take 4 times 27, that'll give us 108. X squared times x to the third will give us x to the fifth, equals our KSP value of 1.8 times 10 to the minus 20. If we divide both sides by 108 and take the fifth root of both sides, we'll solve for x. So x equals 4.1 times 10 to the minus 5, and then we need to go back and double check that we've answered the question. The question wants to know what the solubility of the sulfide ion is. And that value isn't just x, that value is 3 times x. So we're going to take the 4.4 times 10 to the minus 5, multiply that by 3, and that'll give us the concentration of our sulfide ion. So let's look at our next question. What is the KSP of barium chloride if 0.095 grams dissolves in 1 liter of solution? So this time we're going to work the problem backwards. However, we're going to do the same kinds of steps. We're going to write out the equation for the dissolving of our salt in water. We're going to write our KSP expression. And this time we're going to be able to concentrate the molarities and find the KSP. So we've got barium chloride. It's going to dissolve in water to form barium ions and chloride ions. For every 1 mole of barium chloride that dissolves, we're going to get 1 mole of barium ions and 2 moles of chloride ions. So our KSP expression will be the concentration of barium ions to the first times the concentration of chloride ions squared. We can calculate the concentration, so that's done down along the bottom of the page. If we have 0.095 grams of barium chloride, we can convert grams to moles by using the molar mass of barium chloride. And we can take the moles and divide it by the volume to get the molarity. So the molarity of the barium chloride is 4.56 times 10 to the minus 4 moles per liter. It's a 1-to-1 ratio to barium ions, so we'll plug in 4.56 times 10 to the minus 4 for our barium ion. And it's a 1-to-2 ratio to get to our chloride ion. So we're going to have to take 4.56 times 10 to the minus 4 and multiply it by 2, and that gives us our 9.12 times 10 to the minus 4. We'll plug into the calculator 4.56 times 10 to the minus 4 times 9.12 times 10 to the minus 4 squared, and that'll give us our KSP value. So the KSP for barium chloride is 3.7 times 10 to the minus 10. So here's another problem. How many grams of magnesium carbonate can be recovered from 20 milliliters of a saturated solution of that magnesium carbonate? So the first thing we'll do is we'll write the balanced equation for the dissolving of the salt in water. We'll write our KSP expression. This time we're given the KSP. We can calculate the concentrations. And then once we calculate the concentrations, we can go backwards and calculate the grams that were dissolved. So magnesium carbonate will break up into magnesium ions and carbonate ions. It's a 1-to-1 ratio, so our KSP will be the concentration of magnesium ions to the first times the concentration of carbonate ions to the first. We'll plug in 6.82 times 10 to the minus 6 for KSP, and since we don't know the concentration of magnesium ion or carbonate ion, and they're a 1-to-1 ratio, we can plug in x for both of those values. X times x equals x squared. We'll take the square root of both sides, and we get x equals 2.6 times 10 to the minus 3. That's the concentration of magnesium ions in the saturated solution. It's also the concentration of the carbonate ions in that saturated solution. And it's the amount of magnesium carbonate that dissolved in the solution. So now if we know the volume of the solution, and we convert that to liters, we can take the molarity times the volume, and that will give us the moles. So we've got 5.2 times 10 to the minus 5 moles of magnesium carbonate in that saturated solution. And then we can convert moles to grams by using our molar mass, and we would recover 4.4 times 10 to the minus 3 grams of magnesium carbonate from a saturated solution if we were to evaporate away all of the water. Now let's look at another problem. Calculate the barium ion concentration in a saturated solution of barium carbonate. So see if you can do this one on your own. Again, you want to write the dissociation of the barium carbonate in water. Write your KSP expression. You're going to need the KSP for barium carbonate. So I'll tell you that that value is 2.58 times 10 to the minus 9, and that you can just look up on a table. And you want to calculate the concentration. All right, so let's see how you did. We've got our barium carbonate. It's going to break up into barium ions and carbonate ions. Again, make sure you've got the arrow going in 2 directions since it's only slightly soluble in water. And make sure you've got the charges on the barium ion and the carbonate ion. The KSP will equal the concentration of the barium ions to the first times the concentration of carbonate ions to the first. We'll plug in the KSP that we looked up off the table, and that's 2.58 times 10 to the minus 9. We don't know the concentration of barium ion or carbonate ion, but we know they're going to be equal to each other. So we'll plug in X for the barium ion, X for the carbonate ion. X times X equals X squared. And if we take the square root of both sides, our concentration of barium ion, concentration of carbonate ion, and the amount of barium carbonate that dissolved in that solution is 5.1 times 10 to the minus 5 moles per liter. Now, we want to consider what would happen to the barium ion concentration if 2.12 grams of sodium carbonate was added to that saturated solution. So the first thing we need to do is think about what the sodium carbonate is going to do to that saturated solution of barium carbonate. It's a common ion effect. The sodium carbonate is going to 100% dissociate, which increases the carbonate ion concentration, which in turn will shift the equilibrium to the left and decrease the amount of barium ion in the solution. So the first thing we want to do is find out how much carbonate ion we're adding to the solution. So we would take 2.12 grams of sodium carbonate and convert that to moles. So that'll give us 0.0200 moles of sodium carbonate. We'll divide that by the volume, which is 1.00 liters. And that'll give us the molarity of the sodium carbonate, which will equal the molarity of the carbonate ion since it's a 1-to-1 ratio. Now we want to go back to our KSP expression for the barium carbonate. We know that KSP equals the concentration of barium ions times the concentration of carbonate ions. We know KSP is 2.58 times 10 to the minus 9. That number doesn't change because it's a constant. We haven't added any barium ions to the original solution, so that will remain X. But we're adding 0.0200 moles per liter of carbonate ion. So we had X moles per liter of carbonate ion from the original solution, and now we've added 0.0200 to it. But since the KSP value is so small, X, the amount of carbonate ion we're getting from the barium carbonate, is going to be a very small number. Small enough that we're going to be able to say it's insignificant. So now we've got 2.58 times 10 to the minus 19, or 9, equals X times 0.0200. Divide both sides by 0.0200, and that will give us the new concentration of our barium ion, 1.29 times 10 to the minus 7. And if we compare that to the concentration of barium ions we got from the last problem, which was 5.1 times 10 to the minus 5, we're going to notice that there was a shift in equilibrium to the left, which decreased the barium ion concentration.